Alright, so I want to start by proving the height lemma from last time that we left until now. So let me actually first step back a bit and let R of x be a rational function of degree d. And we're going to need a lower bound on the height of R of x in terms of the height of x. So where P of x and Q of x are polynomials of degree d. And let's say they're relatively prime as polynomials. Okay. So we're going to want a lower bound on the height of R of x. So suppose that gamma is an algebraic number. Okay, so we're going to start by writing gamma as alpha over beta, where alpha and beta are also algebraic numbers, and we're going to assume that alpha and beta are relatively prime. Okay, so for all finite v, either this is 1 or this is 1, so they aren't both divisible by this guy, and alpha and beta are algebraic integers. Okay? It's not immediately clear. You can do this. The reason you can do this is because every ideal becomes principal in some finite extension. So you can take the positive part and make it principal, the negative part. Okay. So you can do this. And then if you write R of gamma, that's R of alpha over beta, you can write it in the following way. You can factor it. Factoring P and factoring Q. And just for simplicity, it's not going to matter much, but to make it a little easier, I'm going to assume all of these are distinct. We're not going to keep track of any multiplicities. And we're going to assume that these guys are algebraic integers. Okay? So then what's the idea? The idea now is that if one of these guys is very divisible by some prime, then no one else here is very divisible by some prime. So it sort of dominates that contribution. So the idea now is that if you set D to be the product over ij of Si minus Rj, so D is some algebraic integer, then if V is some finite prime, where some guy in the denominator is very divisible by the prime V, more divisible than D is, then by the triangle inequality, the Archimedean triangle inequality, all of these guys are less divisible than D is by that same prime. Okay? Basically because all the Si minus Rj's are less divisible by that prime. And so it follows from this that if you sum over all finite primes all these log pluses, the contributions from the V place, what you get, well, if none of these guys are very divisible by V, and the contribution is bounded, just in terms of what this D guy is, and if they are, then the top doesn't cancel it out too much. And so, just keeping a few details here, but putting this together, what you get is you can just evaluate these guys independently. Log plus of 1 over this with an error of sig O of the D times the height of the algebraic integer. And note that it's important that capital D depends only on the rational function. It doesn't depend at all on alpha and beta. Okay? Okay, that's also important to us that because alpha and beta are relatively prime, that if this guy is greater than, if this guy is less than 1, so if this guy is divisible by the finite prime V, then beta can't be divisible by V, because otherwise alpha would have to be as well, and we assume they're relatively prime. Okay? So in other words, we can rewrite that expression as the finite contribution to R of alpha over beta is equal to the sum over, there should be a sum over J here as well, right? Is the sum from J equals 1 to D of the finite contributions to the height of, well, here I had 1 over this guy. Now all I'm going to do is rewrite this as alpha over beta minus Sj, because for the V's that contribute, the beta doesn't do very much. Plus the same error term we had before, which I just write as O of 1, something depending only on R. Okay, so basically these guys contribute, the roots contribute almost independently to the height. And I will need an Archimedean variant of this. So now in the Archimedean place, note that if you look at the function log plus of the product of alpha minus Rj beta over the product of alpha minus Si beta, absolute value here. Now I'm looking at the regular absolute value, so the Archimedean absolute value, minus, and now I'm going to sum only over the bottom, so if I look at this difference, then this difference is bounded on P1. This is a function of alpha over beta, right? This is alpha over beta minus Si. So left and right hand side are functions of alpha over beta, and this only blows up near the roots, right? And near the roots it has simple poles, and so does this guy, and so the difference is bounded. So this guy is bounded uniformly with alpha over beta. If I should have log here, I have to be careful because the zeros matter. But I have a log plus, so the zeros don't really care. These functions can't be numbers. Okay. So now, adding this over here, what we get is that the height of R of alpha over beta is equal to, so the height is all of these sums, now sum all of these guys, and so we get is the sum I equals 1 to d of the height of alpha over beta minus si plus big O of 1. Now these guys with the triangle inequality are just the height of alpha over beta, a constant, so I can rewrite this as d times the height of alpha over beta plus big O of 1. Bless you. Okay, so we get the stronger version of what we had last time. We'll only need the lower bound now, but I don't know how to do that without proving the whole thing. Okay, any questions? So I want to point out just one thing, which I find pathological sometimes. In the course of this proof, we're sort of proving that only the denominator contributes to the height. But that's, of course, not actually meaningful, right? That's only true once we sort of write it as alpha over beta and express it as this fraction. If we change the way we express the fraction, then sometimes the numerator will matter, sometimes the denominator will matter. So the individual terms of the sum don't actually make any sense, just the entire summation does.
You have to assume that the two functions in the same degree.
Isn't this true in general?
I'm sorry?
Isn't this true? Like, does the O1 matter here? The specific form of it, like, you know, it's...
You're saying this is true without the O of what?
It's true with O1, but
Yeah.
like, isn't this true in general for any rational function?
Yes. Sorry, so what's the assumptions that I made?
That the degree of the numerator and the denominator are the same.
Oh, it doesn't matter. If the degrees of the numerator was less than the numerator, you would just have some powers of beta here to make up for it. And vice versa, some powers of alpha here to make up for it. So you would just, once you plug in alpha over beta, and you it sort of homogenizes automatically. Right? Like if I had 1 over x, the fraction I get is beta over alpha. And the exponents also obviously can be taken into account. I just want to save the notation. No, this is true for any rational function. All right. Now let me prove the lemma we had last time. So recall what it was. So suppose f of xy is equal to 0, and the degree in the y coordinate of f, I'll just write is equal to d. So then we can write f of xy as a sum y to the d R of x, where the R of x are polynomials in x. Okay. And so now suppose f of alpha comma beta is 0. We want to show that the height of beta is bounded below by the height of alpha divided by d. That was the lemma we had out last time. Okay, so here's how we do it. So first we use Gauss's lemma for the finite places, and what does that tell us? Well, it tells us that for all v not dividing infinity, sorry, I'm jumping ahead. So suppose that alpha 1 through alpha d, let's call this alpha, are the roots of f of x beta equals 0. Okay? So once we fix Oh, I messed this up again. Sorry, I'll fix it this time. 30 seconds. Sorry. Suppose that, that's not what I mean. I suppose that beta 1 through beta d, this is what I mean, are the roots of f of alpha y. Because we know that once we fix the x coordinate, there's only b possibilities for the y. Okay. And that's true because the degree of y is equal to b. Okay, we're in shape. Okay, suppose this, and then I'm also gonna assume. No, let's leave this as this. Okay. So then we're going to apply Gauss's lemma to this guy, and so what do we know? We know that if we look at this polynomial, this is y to the I, r sub I of x. If we look at this polynomial, so y to the I, ri of alpha, we know this can be factored, and rd of alpha times the product of y minus beta I. So we know that the V-ag valuation of both polynomials is the same. And so what does that tell us? It tells us that log of the max of Rj of alpha sub V, which is the V-ag polynomial of this, the V-ag valuation of this polynomial, is the sum of the V-ag valuations of these polynomials. So it's log R1 of alpha, D of alpha, sub V, plus the V-ag valuations of these guys, which is the sum over I of log plus of beta I sub. This is an exact quality, just measuring the V-ag valuation of the polynomials. Okay? Okay. So, likewise, if V divides infinity, and if we look at the maximum coefficient, so V, well, these guys are what? Once you divide by RD, they're symmetric functions in the beta I. So up to a constant, depending only on the degree, in fact, and we get the same inequality. Plus this guy. Okay. Basically, if all the roots are small, the coefficients have to be small as well. That's what this is saying. So then if you sum up all of these guys, this gives you 0 by the product formula. If you sum up all the valuations of something, you get 0. And over here, we get sum over all V of log max Rj alpha. So V is at least the sum over I of the heights of these beta sub i's. Okay? Okay, now if we let M be the max degree, I'm doing this backwards, but that's okay. if you let M be the max degree of these R sub j's, well, these guys are all linear combinations of 1 y, y squared, y cubed through y to the m. So 1 alpha, the powers of alpha from 1 to m. Okay? And we know that y to the m occurs at least once. And so what you can say over here, is this is at most up to a constant, this guy, the sum of log max of 1 alpha, alpha squared, alpha to the m sub v plus O of 1. Basically, because if you, by the triangle inequality, so you sum a bunch of guys up, the most size, the biggest one, up to a constant. And what this is equal to is O of 1 plus m times the height of alpha. Okay? And here we can just isolate the height of beta, because heights are positive. And so we conclude that the height of alpha is at least the height of beta over m plus O of 1. Okay, so I did this backwards. I'm showing you the degree in x is m, then you have this down here. So likewise, height of beta is at least height of alpha will be equal to O of 1. Doing the symmetric argument. Okay? So basically, Gauss' lemma is the way to prove all these kinds of statements. Questions? But I'll point out, we're not going to show it. I think it requires, this part will actually require more algebraic geometry. But in fact, it's, you can get exact relationships between the height of alpha and the height of beta, assuming that f is actually reducible by looking at sort of the height of the algebraic curve is defined. And sort of doing a bit of the theory of heights of line bundles and varieties. If you're interested in that, you can read Barbieri-Gubler's book. But we're not doing that. All right. So now, what I want to do is I want to start on the proof of length conjecture. I'm not going to do it in every detail, but I want to give the idea. So, suppose you have a curve x over q bar, which is inside an n-dimensional torus, and not contained in a proper torus coset. Proper torus coset. Okay? So this is stronger than necessary, as we saw talked about last time. So we showed last time that if you take x and intersect with a codimension 1 torus, and of course you look at points, and those points have heights that are absolutely bounded. Okay? So now we're going to put that to use in proving that x has finitely many atypical ones. Alright, so suppose that z1 through zn is a point in x. Let's call this point z. And z is atypical. Which means that if we look at the rank of the multiplicative subgroup generated by the coordinates of z, these guys satisfy at least 2 multiplicative relations, so the rank is at most n minus 2. Okay? So now, n minus 2 is less than n minus 1. So, by what we did last time, you know that the height of these guys are absolutely bounded. Height of Zi is some big O of 1, depending only on x. Because we showed the heights of, so these guys are finitely many of them we'll show. But the guys with this n-1, their heights are sort of bounded from above, but the heights don't go to 0, right? Because we showed that that can't happen either in the very beginning. Otherwise, that could distribute, and next could be a curve. So the heights really sort of between, are bounded below, away from 0, and above, away from infinity. Okay, so the idea is to bring in some geometry into this. So if you let L be the span of these guys, but we want to get rid of the torsion part, so we consider this as a sublattice of the multiplicative group of Q bar modulo torsion. So we just pretend roots of unit are 0. And then the height function from L to R plus is a norm, which means two things. It means the height of a constant times x is a constant times the height of x. Where times here we're in multiplicative sense, right? So we're differentiating. And the height of x plus y is at most height of x plus height of y. Or again, this really means add an L, so multiply. So this is the triangle equality. Okay. The height gives you a norm here, which means we can bring in the theory of norms in vector spaces. So we're going to let G1 through GR be a Minkowski basis. So I'm not going to go into the theory of Minkowski bases. Basically, you pick the smallest vector, the next smallest vector, and so on. The point is, you can pick a basis like this, such that the property we'll need is that if you multiply a bunch of these guys together with some exponents, and this is greater than some absolute constant, times the maximum AI height GI. Planetary constant, these two are the same. Okay? Alright, so now we express each of the coordinates in terms of these guys. So we write Zj is the product over I of Gi to the M sub Ji. Only we can't quite do this because we might have roots of unity as well in our multiplicative group. And so we have to add a root of unity Zj. And that's going to be important for us. So we're going to record these roots of unity by just saying that if you look at the all n roots of unity we get here, they exactly generate the nth roots of unity. So the common order of all these guys is n. Okay. Notice we sort of also have to prove Lang's conjecture within this proof, right? Because it includes the case where the point z's are just roots of unity. So somehow we have to deal with this case while dealing with this new phenomenon. Okay, so what's the point? Well, we already know that these z's have absolutely bounded heights, right? And so what that implies, using this inequality, is that the g's have very, very small height. Okay? So if we apply this inequality to the z's, what we get is that the height of each gi is bounded above. Well, each j has a height big O of 1. And so for each zj, you can get a bound for the gi of 1 over mgi. And so we take the best one, so we can just write it as bounded above by a constant times 1 over the norm of the vector mj. Okay, which sort of records, takes the best bound automatically. Okay, this is going to be very important for us because the MJ is sort of determine which tori we're in. So these MJ have to get very large if we're to have infinitely many individual points. But the larger the MJ get, sorry, this is GJ, it's bound by MJ. The larger the MJ get, the smaller the height of these algebraic numbers GJ have to get. And small height implies the degree of a Q is large. Okay? And so this is sort of going to give us many Galois orbits. That's the idea for this. Okay. Alright, so far we haven't used rank at most 2, and so now we will. So now the idea is because we have 2 multiplicative relations that are independent, what we're going to do is we're going to find a small, so low degree codimension 1 torus passing through Z. Okay? So we're going to use our 2 independent guys to find 1 small guy. That's the idea. So how do we do this? Well, this is essentially an application of Siegel's lemma. So what do we want? What we want is that we want sort of small integers b1 through bn, so as small as possible, such that this product is equal to 1. That would sort of give us our small torus. And what does this mean? What this amounts to, by sort of these relations, because the GI are multiplicatively independent, what we need is that the sum over I of mji times bi is equal to 0 for all j, so they have to be orthogonal to the mji's. And also that the root of unity part doesn't interfere. So also that the product of zeta I to the bi is equal to 1. So we have sort of our actual linear conditions to satisfy, and we have this sort of mod n condition to satisfy. Okay, so we want a small solution to this. We sort of know the 2-dimensional space of B that satisfies this by sort of abstract by lattice theory. And so what we're going to do is we're going to find the small b. So basically, we're going to reprove Siegel's lemma in this one case. So here's how it's done. What we do is we take a map. We have a map from Zn minus 2 cross mu n, which takes our vector b and sends it to the mj's dot b, and here the product of zeta I to the bi. And we want the small vector in the kernel of this now. I'm just rewriting all of these conditions in terms of that one map. Okay? And so the idea is that if we sort of take bigger and bigger boxes here, the sort of volume, because n-dimensional grows faster than the volume here, which is just n minus 2-dimensional. And so we're going to take B of A to be a box of radius A in Zn, call this phi. Okay, and so the question is, what is the image of phi? Where does this lie in? Okay. Well, if you assume that the mj's were sort of diagonal, you would just get the product of the diagonal entries. of the mj. More generally, the volume here is governed by the co-volume of the lattice that we get. And so this is a bit of lattice theory, but so the volume of phi of b of a, so projected to z(n minus 2), ignoring this guy. So over here, so first of all, the volume of b of a, the number of points here, is of course roughly a to the n, so constant. That's how boxes work. And if we do this here, these were just like bounded entries that get a to the n minus 2, but they aren't. Sorry, this is z to the r, not n minus 2. R is most n minus 2. The volume here is a to the r multiplied by the volume of the lattice, which is the product of the norms of the mj's. Certainly it's contained inside here. This is all a constant. Let me just write this. Certainly it's contained inside here, because that's how big the entries are at the 5 coordinate. And so as soon as a to the n is bigger than a to the r, let's call this quantity v, times v times n, which is the possibilities inside here. So I'm making typos left, right, and center. Soon as this is true, by pigeonhole, we get a small vector b in the kernel. Okay? Soon as this is true, we get a vector b in the kernel of phi. So I'll norm it mostly. So doing some basic inequality stuff. So we can find b with the norm of b at most nv to the 1 over n minus r. Okay? So here we see the benefit of having rank, which is small. Right? The smaller the rank, the slower the volume grows, so the faster sort of you can find something in the kernel. All right. Okay, so once we have this b, we proceed in sort of a natural way. We'll let h be the algebraic torus corresponding to b. So by construction, the point z is an h. Now Bézout's theorem tells us that look at the number of points of x intersect h. This is bounded above by the degree of h, so which is just the norm of b times the degree of x, which is constant for us, but x is fixed, which is bounded above by nv to the 1 over n minus r. This directly gives us a bound for x intersect h. And why do we care? Because on the other hand, the intersection points of x intersect h are Galois stable. That's the name of the Galois conjugates of b. And so what we get, I guess here I'm assuming that x is defined over q, which we do the same way as always. Sorry, we get the degree of z over q, which is bounded above by this, and at most nv to the 1 over n minus 7. Okay, so now we're in position to finish. We have sort of our two basic ingredients. We use this sort of geometry of numbers argument to get an upper bound for the degree of z. And if you recall, we also have a lower bound for various heights, which will translate into an upper bound. And so the idea is to put these two things together. And so this is done using the following two theorems. So there's sort of a bunch of work starting with Lemmer's problem on translating small heights into large Galois. We're not going to be able to, this will sort of require a course in height, so we're not going to delve into the proofs of these theorems. So next week you'll see a proof of like 1 weak variant of these guys. Okay, so first the theorem by Amoroso-David, which says that if G1 through GR are multiplicatively independent in a field of degree D, then the product of all their heights is bounded below by any power of D less than -1. Okay? Which conveniently is what we're going to end up using, to be very relevant. So these we'll just take as black boxes. This is meant to do with intersection theory, with intersection theory or unlikely intersection. This is just theorem about heights. And then there's a theorem by Amoroso who makes a career with these theorems. Sorry, there wasn't a derision. These are very hard theorems. Very hard fought. Which says the following, that if you take an algebraic integer zeta, which is not a root of unity, so its height is not 0, and we're going to get a bound not in terms of its degree, but in terms of its degree over an abelian extension of Q. So we'll let DAB be the minimum over abelian extensions of Q of the degree of zeta over K. K is contained inside Q zeta. Of this degree. Sorry. The minimum over abelian guys contained inside the field that generates of this degree. In particular, if zeta is contained in an abelian extension, this is 1. Then the height of zeta is similarly bounded below by any power of this, is -1. So in particular, this is saying if K is abelian, then the height of zeta is bounded below absolutely. Okay? So this will prove next time, or a rule will prove next time. Alright. So these are the two sort of black boxes we're going to use about heights, low heights translating into high degrees of Galois. Okay. So how to finish? So first we're going to multiply our height inequalities. So remember the height of Gj was bounded below by 1 over Mj, which means if you multiply over all j, the height of Gj is bounded below by 1 over V, by the definition of V. And it's bounded above by this theorem. Sorry. Sorry, this was an upper bound, right? It's bounded above the 1 over V. And it's bounded below by this theorem. It's bounded below by the degree, because they're all contained in Q of Z, by this degree to the -1 minus epsilon. Okay, this is by Amoroso and David. And so we get a bound for V in terms of these guys. So this is all just going to be cleanup basically. The main arguments are done. So V is bounded above by this, I guess to the power of 1 plus epsilon. Not going to be very relevant. And so let me just set this up right. And so what we get is nv to the 1 over n minus r, which bounds above this degree, but also bound above v, which unwinding this gives that n is at least v to the 1 over n minus r minus 1 minus epsilon, which, plugging that back into where am I plugging it back into? Yes, because this is bounded above by this guy. Plugging that in gives you that this degree is bounded above by this quantity. But at the same time, this field contains the nth roots of unity. So this guy is at least n to the 1 minus epsilon. And so we're already done unless r is n minus 2. Okay, so now, unless r is n minus 2. So if r is less than n minus 2, then n is bounded, v is bounded, so there's finitely many options for h, and so we're done. We haven't still used this theorem of Moroso and Zani. So now if r equals n minus 2, then we have no contradiction, but on the other hand, the degree of z over the nth roots of unity has to be n to the epsilon, because inequalities have to be tight up to a factor of n to the epsilon. If this is true, then these degrees have to be n to the little o of 1, which means that the degree of z over an abelian extension is very small, which means that all the heights of all these dj's are bigger than n minus epsilon. Which means, I think I erased the thing I needed. This height is bigger than n minus epsilon. Anybody help me out? Well, which means in particular that v is n to the little o of 1, and then somehow from here you get that everything is bounded. But I forgot this very last step. Well, I want to start. Right, because it's right. So we had that. So n to the little o of 1 is v bounds above the degree Q of Z over Q. Sorry, bounds above this degree, which is at least the degree of n, and so n is bounded. Okay, and so again you finish in the same way as before. Basically everything was stacked, right? So once v is n equal of 1, everything collapses. Alright, so what's the moral? Sort of the moral is you do some clever stuff to get low heights, and then you quote some powerful theorems to get ideal orbits. Okay, any questions? All right.